All right, this next section, 5.8, this is on transcendental functions, some additional transcendental functions. So in particular, we have the antiderivatives for um, um, the ones that turn into the inverse trig functions. So these facts here, there's nothing really to show here. In Calc 1, you should have proven that the derivative of arctangent is this 1 over x squared plus 1. So for us, we are going to use these three facts, and really this last fact here for the antiderivative here, this one's not going to show up. I'm not going to have an example of this. It is true, but we don't have to really worry about that one. So we're going to focus on the first two, 1 over x squared plus 1 and 1 over the square root of 1 minus x squared. Okay, so our goal here, let's take a look at example 1. We start with something that looks very similar to this, but not quite. So we want to take some steps here to bring it closer to looking in that format. So first thing I would do here is just move that dx off to the side. Not that it's necessary to do that, but you do sometimes see people put the dx on top of a fraction. You can always just move it off to the side. So now we have 1 over x squared plus 9, yet the form up here has 1 over x squared plus 1. So we really want to get this 9 and change it into a 1. So one way we can do that is to factor out a 1/9 from the integrand. Factoring out a 1/9, or equivalently, factoring a 9 out of the bottom. So if we do that, what's left over would be x squared over 9 plus 1. We had to borrow that 9 that wasn't present with the x squared. Remember, you can always check to see, did I factor this correctly, based on what do you get when you multiply this 9 back into the bottom. Well, the 9s would cancel here, leaving just the x squared term, and then we'd have a 9 here. So we do get right back to where we started. Excuse me. So now that we have this, what we want to do is change this into the format something squared plus 1. So sure, up here we've got an x squared, but in general, we really want to think of this as 1 over something squared plus 1, d something. Whatever you put in the box depends. Could be x squared, or maybe it's pi x squared squared. It just needs to be something squared. So what we want to do here is express this x squared over 9 as a single thing squared. Well, we can do that by writing this as x over 3, quantity squared. So now that we have this, we can go ahead and perform a u substitution on this. Let u equal x over 3. Then du is 1/3 dx. We don't have a, well, actually, we can think of this 1/9 as really a third times a third. So we can take one of these thirds and group it with the dx to give us our 1/3 dx. So that's a lot to say right there. So let's actually write this out. It's not necessary really, but it'll make it a little bit clearer for some. There we go. So now we have this term collectively. That will become our du, and this term here will become our u. So this entire integral becomes 1/3 the integral of 1 over u squared plus 1 du, and as soon as we have it in that format, we know that it is arctangent, or inverse tangent, of u. And then back substituting, we have 1/3 inverse tangent of u, and we chose u to be x over 3. plus c. So most of these problems is a lot of algebra to get it to look like something squared, plus 1 in this case, and then we want to perform a u substitution. So in this section, it's still just u substitution, but there's a little bit more algebraic manipulations that have to take place before we can perform the u substitution. Okay, so for part B, this integrand 1 over 3x plus 4 does not look like either of these. And this is sort of like a red herring. It's trying to check to see, are we still remembering all of the other rules and forms of antiderivatives? So in particular, we should remember that 1 over u du, when we integrate such a thing, this is natural log absolute u plus c. So here, because our inside function, the downstairs, really u is 3x plus 4. So this inside function, 3x plus 4, it's a linear function. So we can take the shortcut for anti-differentiation where we can just integrate it by leaving the bottom alone. So natural log absolute 3x plus 4 plus c, but because this is a linear function, we have to divide by that derivative. Think of it as undoing the chain rule. So 1/3. But this is a definite integral, so we don't actually need this plus c. We really need some evaluation bars with 2 and 12. So this is 1/3 natural log. 12 times 3 is 36. 36 plus 4 is 40. Minus 1/3 natural log of 6 plus 4 is 10. Now each of 40 and 10 are positive, so these absolute value bars are not really necessary at all, so we can drop them at this point if we'd like. I'll factor out a 1/3, and we're left with ln 40 minus ln 10. Natural logs have the property that if we're doing subtraction, we can convert this into division of the arguments. So 40 divided by 10. So this is 1/3 natural log of 4. And that's it.